The AVO Valve Tester thing. Everybody knows about AVOs, everybody knows they're just great. Okay, patented in 1936, okay, that was a long time ago. Back then, someone probably said, yeah, but if you want to test valve characteristics, you've got to have a regulated anode supply, so that doesn't shift under test. Regulated screen, that'd be good too. Regulated grid volts, so we need 3 regulated variable DC supplies back in 1936. Well, there was probably one in a laboratory somewhere in England, but you can bet that that was like suitcase size. So, David MkIV, the guy who invented the original AVO amp volt ohm meter, said, nah, not going to bother. We'll let the valve do the rectification. We can make good transformers that we know when the load comes on, we're going to get out pretty much the voltage we dial up. So we're not going to bother with a regulated DC supply, we'll have a regulated AC supply. Valves are good at rectifying, we'll let them do it. One peculiarity is that whatever setting you see on the dial, let's say it's showing 60 milliamps, the actual current in the valve is only 30 milliamps. And the reason for that is that the valve is only conducting on the half cycle. So it's exposed to the conditions that it would experience on DC with say 200 volts, 60 milliamps, and it will give the transconductance reading for those conditions, but it's only doing it half the time, so of course you only get 30 milliamps instead of the indicated 60. So that's one of the mysteries that you look at and you go, oh, okay, that makes sense. Now, it uses what I call a suppressed zero. If you've got a voltmeter on your car or some piece of portable equipment, a 12-volt battery, you don't need a 0 to 16 scale, right? What you really need is like about 11 or 10 to 15, because you're not interested in anything below that. Well, likewise, if the valve's drawing 45 milliamps, I don't really care. I'm not interested in that. I'm interested in what happens if I shift the grid voltage by 1 volt. I don't need to know that it starts at 45 or 43 or something. I need to know what the actual increment is in anode voltage when I jiggle the grid volts. So on test, we set the valve up, we reduce the grid voltage by 1 volt effective. Again, if you read through the documentation, you won't find 1 volt measured anywhere. That's because we're dealing with half-wave supplies and we're dealing with average values. So the average value of a sine wave, I think, is 0.63 of peak. Okay, so the maths is a bit eye-watering. Just realise that as far as the valve's concerned, it's experiencing exactly what you see setting on the dials, and it's giving exactly the readings that you see on the dial. So, reduce the grid voltage, the anode current's got to go up, right? And if we've got 1 milliamp per volt, 1 volt shift on the grid will give 1 milliamp change in anode current. If we've got 2 milliamps per volt, 1 volt on the grid gives 2 milliamps change, 4 milliamps, 1 volt on the grid gives 4 milliamps, and so on. So what would be nice to get is an actual reading in milliamps per volt, rather than having to do mathematical calculations. So the meter deflection either shows the merit figure on a 0 to 100 scale, is it 100% good or maybe even better, or what I'd like to know as an engineer, what's the actual GM value for this valve in case, say I've got an amplifier that has to have 2 matched valves. If one's 3.8, I want another one that's 3.8. It doesn't have to be 4, as long as they're both the same value. And by reading the GM value directly, I can match valves up. So this is the original valve tester. Looks like a multimeter, doesn't it? Well, pretty much. It's just a big multimeter with a whole lot of stuff inside. You won't find many of them around still. I was lucky enough that one of our former members, Enes Selimovic, had one, and he said, would you have a look at it? I said, love to. So that's where I got all the stuff from the valve tester for. So this is 1936 technology, and at the time, everyone went, wow, that's pretty amazing. So, let's say I haven't got one, I've got a multimeter, I'm good at measuring things, so I set up a valve with 200 volts, blah, 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 and I find I get a current of 45 milliamps. But is that, gee, I guess it is. Yeah, all right, let's say it's 45 milliamps. Then I shift the grid voltage by 1 volt. Great. Now what's happened? How much increase did I get in current? hang on, it was sort of 45-ish, and I think it was about, I don't know, 49. I can make a bit of a guess, maybe that's 4 millisiemens or 4 milliamps per volt, but I haven't got a very good reading. It relies on my reading accuracy and the instrument. What I'd like to do is this. I'm going to suppress the zero. The valve's drawing current, but I don't care. I don't even want to know about that. I don't want to know. All I want to know is, can I set the indication back to zero, suppress zero. Now I'm going to apply a 1 volt grid change. Boink. Oh gosh, it's 4.1 milliamps per volt. It's a 0 to 10 scale, and I can need, in fact, you can probably pretty well determine that's 4.1 milliamps per volt. A bit more than 4, a bit less than 2, halfway in between. So that gives me an actual explicit reading of the transconductance. Alternately, I might just have a whole bunch of valves. I'm not fussed about the actual transconductance. I just want to know good or bad. So I'm going to go for a merit test. Again, I'm going to crank it back to zero. Indication with my backed off suppressed zero. And what I've done is I've set one of the controls for the GM reading to be 4.1. That is, although I don't know it, I'm reading 4.1. All I want to know is it good or yep. It's exactly 4.1, but I don't even know that. I assume because I said it, that's what it is. More importantly, I've got a direct reading of the valve's merit. And if I plug in a whole lot more with those exact settings, I'll find some will come high, some will come low. But I know that one at least does match exactly the GM that I've asked it to provide according to the settings. Just check my notes. So that's the basic principle of the AVOs, all except the 163. So the whole lot of them, you set the valve up with the correct parameters, voltage, current, blah, 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 blah. You then use the backing off control to suppress the indication from your direction, suppress the indication back to zero. Great. Don't care what the actual value of anode current is. Then apply a 1 volt grid shift and see how far up the meter indication comes. And like I said, you can either do that as a direct GM reading, if you want to get actual values for the valves, or you can do it as a merit reading if you just want sort of good, bad, 80%, whatever. Okay, so here's the valve tester. The good old basic 1936 version. There's a meter. Well, gosh, it's indicating anode current. Well, of course it would, because I've set it up with anode voltage, screen voltage, and I'm on the set condition. So here it is sitting and giving an anode current. Well, I really don't care what the anode current is, because I'm interested in how good the valve is. A couple of supplies here. There's the anode voltage supply from the tranny. Yep. A screen voltage supply from the tranny. And there's a grid voltage supply, which is effectively negative half cycles. There's also this other supply, but at the moment, that pot is dialed all the way up to zero, so it's going to have no effect, yeah? So at the moment, the backing off circuit has no effect, and I just get maybe 45 milliamps of anode current, which is exactly what you'd expect by applying voltages to the valve. Now, what I'm going to do is I'm going to apply the anode current to the valve through this secondary path. Okay, so all the anode current to the valve is being supplied through that secondary path. So how much flows in the meter? Zip. What's the meter do? The meter drops back to zero indication. So this is my zero suppression circuit. And that's how it actually works. All it really does is to supply an alternate path for the anode current. So now what's going to happen is the anode current, still 45 milliamps, is not going to indicate on the meter. Great. Well, now, and this is the tricky bit, what I've done is to invert the grid voltage. It's now plus 0.5. So from, where were we? From minus 0.5 to plus 0.5 is 1 volt. So it's effectively a 1 volt change in grid voltage. What that must mean is that the meter will deflect. I've still got 45 milliamps through the back-off supply, but I've now got another 4 milliamps because the valve's kicked up to 49. Okay, so that's the valve tester circuit, the old 2Ks model, and that's really all it is. If you have a look at the circuit, the only thing that's added is just a whole lot of bits and pieces. So that's the fundamental design of the circuit. The backing off supply effectively bypasses the standing anode current, and then when you hit it, the grid voltage change, the extra current is read as an increase in the meter reading. So, worked well. Why doesn't anyone still use it? Well, it set the standard. That is where everybody goes back to and says, oh, the AVO, blah, 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 probably not realising that you actually have to go back to like the mid-1930s, which is when they must have been conceiving of it, to see where the germ of this entire line of test equipment was. Able to test filament voltages from 1.4 to 40 volts, that's pretty handy. You can even theoretically do your 1S53 V4s on the original valve tester. Able to measure up to 100 milliamp per volt. There's virtually no valves apart from specialised secondary emission things that do it, so it'll test pretty much any valve you can think of. However, there's no mains setting indication. So, are you applying the correct specified voltages to the valve? Maybe you are, maybe you're not. You've got no idea. There's no way you can tell whether the mains setting is correct. There is a set of taps on the inside of the instrument, but that's it. If you're set for 240 and your mains is coming in at 210, you've got no idea that's the case. So no main setting indication, which is really pretty important. Limited range of anode and screen voltage settings. It goes up to 200, 250. Anyway, it doesn't go all the way to 400. It tests at zero grid bias. Now that's a problem. That's okay for something like an O1A or all those older tungsten or thoriated valves, but you won't find an oxide cathode valve in the valve catalogue where the manufacturer says grid voltage 0 volts, blah, 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 blah. Every oxide-coated cathode valve you find will be specified by the manufacturer at some negative grid voltage. So, no good for modern valves. In fact, the actual settings in the book are quite different from ordinary manufacturers' recommendations. It may still be a useful indication, but it's not testing under optimal conditions. And the grid voltage swing's positive. So you potentially have grid conduction happening, which is a bit of a no-no. The valve's probably okay, but I don't know how good the actual measurement is. And like I said, it's not suited to oxide-coated cathode types. So they revised the whole thing and came along with the Valve Characteristic Meter. There's two distinctive types. There's the Mark 1, Mark 2. This is the Mark II. It's got the front handles, and usually it had a tray underneath for the valve data book and those two skids underneath. The Mark I didn't have the front handles, didn't have the skids or the tray. The Mark IV, which is the last of the what I'll call sort of electrical ones, has those windows over the control dials. They've both got a very convenient front sloping case, and they've got the valves sockets on top. That one, there's a flap to stop debris and stuff getting in. This one, they're protected by that rollover cage. So then, that was okay. But that's a large laboratory style instrument, and with both of them, what you had to do is set up all the valve parameters, then manually back the thing off, then go to the conductance reading, and hope that in between setting the backing off and going to your conductance reading didn't bump anything and change the anode current. Large and sort of complicated. So, mains voltage setting indication, yes, got that. Variable grid bias, yes, got that. You can test at the manufacturer's specifications. Extended anode and grid voltage settings, up to 400 volts. Coarse and fine backing controls, rather than just a single one, which is always a bit difficult and dodgy to do. And it's got an explicit diode test function on it. So if you're testing rectifier valves, you can test them as well. So there's a couple of differences. The 1 and 2, and these are in the notes, retain that bypassing anode current back-off circuit from the valve tester. They didn't change that. They also, for the anode current user, it looks just like an ordinary milliammeter with switching shunts like you'd see in a multimeter. Works okay, but it's not completely reliable because you've got that switching of the shunts. The Mark 3 and 4 didn't do that. They just used a fixed 200 ohm resistor and did all their measurements across that. Much more reliable. And as well as that, they used a voltmeter design for the anode current meter, so you're just switching series resistors in series with the multimeter. Again, this is all in the description, so if your head's spinning at this point, that's okay, just have a bit of a look at the notes. So here's the basic for the 1 and 2. Oh, sorry, I'll just pause there. So how are we doing? You're either completely bamboozled or you're following me okay. Please, you're following me. Okay, next one. So here's the Mark 1, Mark 2 basic. There's still this backing off supply that bypasses the measurement circuit for back off. But what they've done now, the most important thing is there's a variable grid supply. Instead of that manky old minus half a volt plus half a volt AC supply to the grid, there's a really neat variable grid voltage supply being supplied to the valve. As well, they've put in the famous overload relay. Now, that's a bit of a curious beast. Usually a relay doesn't stay latched in unless it's got power, yeah? Okay, good. Then most like that. This one has a magnetised core, so the armature will stay just locked in due to the magnetisation. That's okay. If you then put a current through the relay coil in the right direction, it will lock in even harder, and that's fine. If you get current going the wrong way, it will throw the magnet out and it won't reset because the magnet's not strong enough to pull the armature down. Again, there's a description in the notes, but that is protection against short circuit. How's that? Well, the relay will throw out if it's got the wrong direction of current coming through it. Let's say you've got a short and you get a positive half cycle. The relay will pull in really hardly, but as soon as the voltage goes negative, you'll get a negative current, the relay will throw out and you've got to go and reset the instrument. So that was an important change because it protected the meter and it protected all the other circuitry. But those were the only two real changes in the Mark 1 and Mark 2 electrical circuitry. There's the variable grid bias, so you can test at the correct grid voltage for the valve, and there's the overload relay, which protects against short circuits in the valve or just setting up all the switches wrongly. So, here's a Mark 1, Mark 2 backed off, and again, all we've done is supply anode current into the valve and bypassed the measuring circuit. So again, the meter just gets adjusted back to zero indication. In this position, it's in set and I've got the most negative voltage available. If I go to test, I switch to the test position, the grid voltage is less negative by a volt. So the anode current will increase, the meter deflects, you read off the GM. Okay, pretty simple. Making sense? I've got a nod, one nod will do. Great. Yes?
Where are those stats you're talking about?
They were on a chair just by the door there. If you've missed out, ping me off an email and I'll send you the PDF. There's also a two-part article coming up in Silicon Chip, a month or two. Coming up, so it'll be repeated there, but the notes are more complete than the Silicon Chip articles. Okay, Mark 3, Mark 4. This is the pinnacle of the sloping front all electrical designs. What have they done differently? Oh my God, okay. All right, let's do the easy bit. Yes, they've still got the negative grid supply. Okay, no frights there. Yes, they've still got the overload relay, no fright there. They've still got that diode on the screen to make sure the screen never goes negative. Okay, that's all good. What else have they done though? Well, they've still got a backing off circuit. But this time it's not supplying current into the valve. This time, the backing off circuit is applying a voltage to the meter which counteracts the voltage across the 200 ohm series resistor. Again, there's more in the notes. That's rather neat because nobody likes switching current because you get arcing and splats and stuff on the switches. What people like to do is switch voltage. So effectively, it is now a millivolt meter reading across the anode current sensing resistor. And at the moment, there's no backing off applied. I've got that pot set to 0, that pot set to 0. There's going to be no effect on the backing off. If I go to backing off, okay. So now I've applied enough voltage there that the voltage drop across the meter side to side is 0. So the pointer is going to fall back to 0. Yeah, that's what we've been doing all along. It's the same suppressed 0 thing. It's just that now instead of fiddling with anode current, I'm working on the meter circuit directly. All right, that seems to be working pretty well. So we've got it back off. Have we? Yeah, we've got 241 volts that side. 241 volts that side is 0 volts. Meter goes to 0. All right, now what? Well, now what I'm going to do is I've changed. I've got a slightly less amount of negative voltage on the valve. Let's just check that. In the backed off condition, I've got 0 there and minus 12.5 setting, and that's the setting I would have set on the grid voltage control on the front panel. But I've got this funny little minus 1 volt thingy here. So the difference between minus 1 and minus 12.5, because I've reduced the grid voltage by that 1 volt, I've only got 11.5 volts now. I've got 49.1 milliamps. That means that I've no longer got 0 voltage drop between the two halves of the meter. So I'll get a direct indication of the transconductance on the meter. Alrighty, so, well, look, that's all very well. I mean, everyone loves the big ones. Actually, Mark IV, can you read those dials? Man, red printing on a black background, okay? Just saying, don't do it. However, what some people wanted was something they could pick up and run away with. Bang it on the bench, do a couple of valves, close it up and run away with it, throw it in the back of a Herc and away you go. So we've got the CT160. That's the one that I call the clamshell. Ready and reliable testing, widely used by the military, and you've probably seen it in civilian applications as well. We had on all the radio workshops I went to in the Air Force, there was a CT160. In fact, for a long while I thought that was the AVO. It's not, but there's only one peculiar thing about it though. All it really does is measure transconductance. It doesn't give you an indication of anode current and stuff. It measures transconductance directly. Now you can use it to chart valve characteristics, but it's a bit of elephant and castle thing. What it's most useful for is you've got some valves, you just want to find their transconductance, and that will give you the direct indications. They do things a little bit differently. There it is, the old clamshell. The circuit, well, it looks vaguely the same. Let's check what they didn't change. Relay, love a relay. Grid supply, a little bit different. Not sure about this one, but it's still got grid volts, that's good. It's got this really weird looking, no, it's about the same. It's got a backing off circuit, and it's got the 200 ohm sensing resistor, so maybe that's around about the same. The only thing is that it doesn't have any backing off controls, or they're not labelled that way. The backing off controls are labelled anode current. Well, I suppose that makes sense, because before we were reading 45 milliamps anode current. In this instrument, when you dial up the anode current, it applies the counteracting current to the valve and the meter indication drops to 0. It's just that they don't call it backing off, they call it anode current. So, yeah, you turn it on, no backing off, blah, 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 meter indicates anode current, lovely, exactly what we expected. What if I go and do the backing off? Well, the backing off applies a counteracting voltage to watts across the 200 ohm resistor. 241 on that side, 241 that side, got to be 0 volts on the meter. It's going to go to 0. Of course it is. Exactly what we wanted. So again, it's that basic AVO principle. If you back the meter off to 0 indication, and then you see what happens when you increment the grid voltage. Let's do that. I very sneakily crept that one up a bit. And now, instead of what I had previously, which was minus 12.5, and this is going to seem really picky, but it's a tribute to the precision of these designs. I've gone from 12.5 volts on the grid to 12.37. Sounds a bit odd, I've only changed it by 130 millivolts. If you read the detailed description, that will all make sense. The thing is, the meter sensitivity is fixed. You don't get to change it from 5 to 25 to 100 milliamps. So because the meter sensitivity is fixed, the grid voltage for various transconductance ranges or readings has to be changed. So that's the sophisticated bit in the 160. It's always got the same full-scale meter deflection. That never changes because the meter is not shunted. It's got other bits and pieces all around it, but the meter itself has no adjustable shunts. What does change is the grid voltage is changed according to the setting on the transconductance dial, and the setting on the transconductance dial is calibrated so that if the valve's got 4.1 millisiemens and you dial to 4.1, you're putting a voltage that's just enough to bring the meter to the correct indicating point. A bit complicated, like I said, it's in the notes. What's important is for the CT160, you are only measuring transconductance, and although you don't know it, your adjustment of the anode current controls is doing the backing off to 0. It's probably pretty obvious once you look at it and go, yeah, okay, that's taking the meter back to 0, and that's the backing off circuit in that one. Okay, pretty robust, you know, it's, like I said, chuck them in the back of the hurt with all the other tins and stuff, and away you go. So then they looked and said, okay, we've still got this meter. If everything goes wrong, you're going to have a lot of current through the meter, you're going to overswing it, maybe in worst case burn it out or pop the coil out of the mountings. Why don't we do it the smart way? So they did. The VCM163. Firstly, it's got 1 meter for anode current, it's got a separate meter for milliamps a watt, so you don't have to switch and back off and all that stuff. I call it the ultimate AVO. It measures electronically. There's a small signal generator inside the instrument, puts out, I think it's 14 kilohertz, it's quite a high frequency signal, and that goes onto the grid. You can even think of it as modulating the grid voltage. Then, that must produce a 14 kilohertz signal across the anode load resistor, yeah? So it's just operating as a voltage amplifier. But it's operating as a voltage amplifier. You know what voltage you're putting in. You can find out what voltage you're getting out across the anode load resistor at 14 kilohertz. So, let's do it this way. We have a signal generator going on the grid, and we get the grid voltage, and a close-up of the grid voltage would show that it's modulated by this high-frequency signal. Bit of AM. At the anode, we must also get the anode current being modulated by that signal. Great. What about I filter out that high-frequency signal, amplify it, rectify it, boom, off I go. I've got a direct reading of the transconductance at the same time as I can measure the anode current and fiddle around with anything. I don't have to back off, I don't have to switch back and forwards. And as well as that, because the meter, or at least the transconductance meter, is not in the direct current path, that's much less likely to get damaged and overloaded. Okay, so that's the basics of the instrument. Any questions?